Howdy and welcome back. So let's go ahead and get into our implementation, how we're going to code up a graph using the adjacency list representation today. So to keep things simple, as I alluded to in the previous video, we're going to implement a graph in a way that's memory inefficient, but hopefully easy to understand. So the circles here are going to be our vertices, and the solid lines connecting between them are going to be edges. How we're going to encode the vertices within let me step back. How we're going to encode our graph is going to be as a standard library map that is going to map a string, kind of serving as an index, to the value, a standard library list composed of standard library strings. So our collection of vertices will be stored as map keys, and our adjacency list encoding the edges will be stored as the values that are mapped to by a respective key. So why is this entirely memory inefficient? Well, let's look at this yellow. I guess I'm coloring it a different color. Let's see, yellow. So that one right there, just highlighted it a little. We're going to store that vertex as a key in graph. Okay, that key is going to map to a standard library list composed of other strings. So we can see here that this connectivity here and here is represented through entries to yellow's adjacency list. And then keeping in mind that this is an undirected graph, what we're going to see is there's also going to be entries for those connection in blue and purple's respective adjacency list. So why is this memory inefficient? Well, if we look here, yellow, the string yellow, string is encoded 3 times. Just kind of seems like a maybe waste if this was a larger typed object than a string of a few characters. So that's why this representation using addresses might make a little bit more sense, because we're not storing the object redundantly or many times within our representation. But today, this will keep things super simple. So we're going to continue today's lesson using that representation. So we're going to go ahead and implement a class called undirected graph. It will have 3 data members, the first being the graph that I described on the previous slide, the second being the number of vertices presented or present within that graph. The third and final will be the number of edges within our graph. These are simply counts. So if we add a vertex, we'll go ahead and increment number of vertices by 1. We put in an edge. Since this is an undirected graph, for instance, if we were putting the edge between, clean this up a little, creating an edge between purple, trying to get some colors that stand out here. So purple and yellow. Since this is undirected, that edge will get stored both within purple and yellow's adjacency list. Okay. The functions or behaviors for undirected graph type are going to be a default constructor, which is going to have very limited behavior. It's effectively going to initialize number edges, number vertices to 0 and default construct that standard library map. And then we'll get into some more interesting behaviors, such as the addition of a vertex into our graph, and then creating edges between vertices, and then 2 more straightforward functions that will answer questions such as our 2 vertices neighbors, and then also, which in this last one will be helpful for the subsequent lesson when we start talking about graph exploration and searching, effectively coming up with a way to ask the graph for all of the neighbors or all of the vertices adjacent to some vertex V. Well, let's go ahead and continue on.